Okay, what we're going to see today is all of Chapter 7. Alright, so Chapter 7 we're looking at reactions of alkynes. Alkynes, if you remember, are triple bonds. Alright, first thing we're looking at is nomenclature. We're going to see that the rules for nomenclature pretty much follow along exactly how alkenes did. Alkynes are just actually changing the backbone name. So what we have here is the YNE. The YNE is just actually replacing what an ENE is. Now, whenever we have the alkyne or the triple bond in the backbone, we're going to follow the rules very much like we did with alkenes. We're going to number our backbones so the triple bond has the lowest possible number. Now, when there's a tie, like in both these cases, our triple bond starts at either the 1, 2, 3, 4th position or the 1, 2, 3, 4th position. Since it wouldn't matter on that, then we look at our other substituents. And that's what happened on this other one. We're getting at the triple bond at the 3rd carbon either way we go. So since that bromine's off this end, we end up calling that our number 1 position. Alright, so for practice, what we're going to look at is these wonderful little molecules here. And first thing is always the same. We're going to find that longest backbone. We just want to make sure this time it includes the triple bond. Alright, so we have 1, 2, 3 before we get to the triple bond, or 1, 2, 3. Alright, so we have a tie, so we look at our second set of things, the other substituents. Therefore, we're going to call this our 2 position. So we're going to have 5-bromo, 2-chloro, 2-methyl, hexyne, and we're going to put a 3 in the middle to specify where the alkyne is. So we could have actually done 5-bromo, 2-chloro, 2-methyl, 3-hexyne, but we're going to see that we're going to put it in the name sometimes. Got this as our backbone. The bromine's there to throw you off because we're not going to decide our numbering based on it. Our triple bond, it's better to have that start at the number 2 position. So 5-bromo, 2-pentyne. That way we have our triple bond number as part of the backbone. Now our final one's drawn a little bit more like how this first one should have been. And that's mainly because the triple bond has bond angles of 120 degrees. So that is a carbon there, and that is a carbon there. And then there's other carbons on this. But that's how we'll typically see it drawn. That puts our backbone something like this. And then we'd have a triple bond beginning at the 4th carbon or the 4th carbon. Since it's a tie, we're going to let the bromine decide it. Two bromo, 4-octyne would be our molecule. Okay, when we have double and triple bonds present, neither one of them necessarily take precedent over each other. So what we're going to end up doing is actually just finding the one that's the closest to the beginning. So since we have a triple bond starting at this position, we're going to say that's our number 1 position. 2, 3, 4, 5 here for the double bond. So what we have, since it is a hept prefix for 7 carbons, we have a hept-ene-ine. We're always going to order them as ene first, ine second. So we have to put these with the numbers in the backbone. So this is a hept 5-ene, 1-ine. Now, since it doesn't take priority on the next one here, the double bond's going to be the lowest number because it starts on that 1st carbon. It's another heptene-ine, but now it's hept 1-ene, 5-ine. And on the last one there, since the double bond and triple bond must be the backbone, that is our backbone. Therefore, this thing is a substituent. We're going to number it based on the double bond and triple bond. So that is going to be our first carbon. So we have a 3-butyl. And then it's a hexene. So hex, 1-ene, 4-ine. Alright. Now, next thing we're looking at in this chapter is the functional group priorities, and we're only focusing really on the ones that we've looked at so far. So far we've looked at double bonds and triple bonds. We've looked at nomenclature for amines and alcohols. Now we're leaving this up here because we're going to have a much higher priority. But basically what this says is when we actually name a organic molecule with multiple functional groups, the backbone name actually must include the one with the highest functional group. So, yeah, we're going to start with a simple thing. It's got nothing like an alkane. And if we do a double or triple bond in there, that becomes the last name. So what I just made down there, I took my butane and I turned it into 1-butyne. But if I come here and put an OH or an NH somewhere else in the molecule, since the OH has higher priority, that becomes carbon number 1. Always the higher priority is going to override the numbering. Now, we're going to add to this as we build up. Right now we have just the basic, the lowest priority ones. Now, I have this table. It's very incomplete, but it has the ones we have. And what we have on here is the suffix that we're going to use when it is on the backbone, and then a prefix we're going to use if we have to make it as a substituent. Now, we've actually done all of these prefixes down over here, and we'll be adding to these a little bit later on. That's basically what we're going to do if it makes more sense to have the OH as a substituent or the NH as a substituent. So we're going to expand on these prefixes, but right now we're looking at what happens in the order of things when we put multiple functional groups in a single backbone. So a great example of that right here. So what we have on this first one, we have our carbon backbone, and that includes the double bond and the OH in it. But since the OH is a higher priority, that's going to be our number 1 position. So what we have is a propanol. So it's a prop 2-ene 1-ol. We're having both of those substituents, or both of those backbone names in the name itself. Got another one of these, so it's an ene-ol. But we're going to have the OH at the highest priority, so it's the number, it's going to be closest to the beginning of the chain. So I actually have, in this case, have 4-methyl pent 3-ene 1-ol. Now I do want to skip down to this one here because I want to show that the OHs don't always have to be at the 1. Both of these cases they were, but on this one down below, the OH isn't in the 1 position, but it still actually dictates how we number it. Since the OH is the highest priority, I want it to have the lowest possible number, so I'm going to start numbering at this end, and it's at the 2 position. So we have a hexenol, but this is hex 3-ene 2-ol. One we skipped up here is an amine, because it has that nitrogen on it. Now it is just an NH2, so we'll have none of those none of the substituents coming off of a capital N, but we do have to keep in mind that this has a higher priority, the nitrogen that is, over the double bond. So that's at the 2 position, 3, 4, 5, 6. So we have a heptene amine. So what we have is hept 2, or sorry, that should be a 6. Six-ene 2-amine. Alright, on our two rings, the highest priority functional group will get the number 1. So in this case, that means the OH is the number 1. And then we're going to number it so we have the lowest possible numbers. I'm going to have my double bond start as 2, 3, 4, 5, 6. Alright, so our backbone is a cyclohexene-ol. So we just have a 6-methyl cyclohex-2-ene 1-ol. Now, interesting, we'll sometimes see that called 6-methyl cyclohex-2-enol because the 1 is actually somewhat dictated by the fact that it must be the number 1 position. On our last one here, the amine, I'm going to put that as the number 1 position, 2, 3. So I have a hexenamine. So it is a cyclohex-3-ene 1-amine. Alright. Last little weirdness that pops up. Since the double bond and triple bond have the same priority, when they're actually a tie, we actually have to have a tiebreaker. So what I mean by a tie, I either have the double bond starting at 1 or the triple bond starting at 1. Normally we would just actually go with the one that starts at the lowest value. In this case, it doesn't make a difference. So when there needs to be a tiebreaker, the alkenes take priority. So the double bond is the number 1 position. That's a 4. And this is starting at 6. So what I have on this case is a 4-methyl hept-1-ene 6-ine. And my last one here, my backbone is the enol or ine-ol. And we're going to put the OH because it has a higher priority at the lowest possible value. So I have hex, 4-ine 2-ol. Alright, enough with nomenclature, on to some reactions. Now our reactions are going to center around the fact that that triple bond is very, very rich in electrons. It is actually very nucleophilic. You can see that in our electron density map, but that should also make sense because a double bond or a pair of pi bonds is going to have a lot of electricity, so is the sp hybrid orbital. So those electrons are actually going to drive the reaction. It makes it a very reactive center. Now when it actually reacts, we're going to find that it's actually slightly less stable than an alkene. Now it's going to pay off quite a bit in our reactions because since it's actually much less stable, anytime we actually do a reaction that's going to get enough energy to make an alkyne turn into something else, that's typically going to have enough energy that it actually keeps on reacting. What I mean by that is it's very hard to turn an alkyne into an alkene because since the alkynes are so much less stable, when you actually do one reaction that maybe turns it into an alkene, the conditions are ripe for the alkene to keep right on reacting. So it's more of a cascade reaction. Okay, what I mean by that is we have some stability issues with this. Now, if we were looking at just a double bond and we wanted to add, do like the first step with an H and do the carbocation, we actually create a carbocation that, in this case, could be secondary. Now, when we have that as a triple bond, a double bond has so much still electronegative ions in there, or it's still very nucleophilic, that having a cation charged onto it is very unstable. Matter of fact, the vinylic cation is very, very unstable. It's almost as unstable as just a primary one. And what I mean by a methyl cation. So remember how this was so unstable, we pretty much say it doesn't actually do much. The vinyl cation is about the same problem. So what we're going to do is expand our stability chart. We're going to add our vinyl position. Oop, too far. We're going to add some vinyl positions onto this, and we're going to see that they are very close in that low stability. We're going to find that for the most part we don't really do much with carbocations except when they're at this end. We have to kind of force the other ones to actually happen. So vinyl cation is not very stable at all. But in our reaction mechanism, we can predict some better stability when we actually keep in mind that the H and the Cl don't necessarily need to break. So what we are showing here is that the H and the Cl, the electronegativity of the chlorine, is going to help stabilize this complex. We actually call it a pi complex. Now, if this occurs, though, we're going to actually end up with an anti-addition, because what we're going to have is another chlorine coming in from the opposite side, and it'd have to come in from the opposite side because we have that positive there. But we're going to find that that's a difficult thing to prove, because it turns out, back to the stability, if the reaction conditions are favorable to have this go forward to make an alkene, they're incredibly favorable for the HCl double bond to go on and react with a second HCl. So what we're going to find is we really don't see this last, because another HCl is going to add to it. We'll put the H with the side with more H's. And put another chlorine with the side that has one chlorine already. So it just keeps right on reacting. It's way too reactive to stop. Alright, so that actually shows us our first little dilemma we're having. Whenever we do an HX addition, like with our alkenes, we actually do favor making a Markovnikov product. If you notice, this doesn't actually make a difference. Neither side has more H's. So we just arbitrarily decide to put the H on one, the C on the other. But since this is more stable, it's going to continue on to react with the more reactive HCl. So if the reaction conditions were actually enough to make this react, this is definitely going to react. So this is basically more like saying we're going to do HCl in excess. It's the only way we can guarantee we're going to get one product and not an overall mixture of products. Now we have a weird term that pops up. Since the H on that, the HCl on that second one, the H is going to go to the side that's more electrophilic. This is just like our Alkynes chapter. We're always going to have the H go to the side that got the first H. So therefore, both of our halogens end up on the same carbon. We use the term geminal to say that. Geminal just means that they're on the exact same location. Mechanism of that and how we draw it out fully, it looks something like so. So our nucleophilic triple bond attacks the H. We transfer electrons to the chlorine. We make this temporary pi complex that allows a nucleophile, the chlorine in this case, to attack from the backside. And we get a substituted alkene. Now in this particular one, we are seeing a Markovnikov product. I have one of these positioned with more H's, and we can see why that's more stable if we look at what that transition state must look like. And what I mean by that is we have a very electropositive hydrogen attached to the ring. Positive doesn't really go in the ring like it did before. It stays on that hydrogen, but it does make that ring attractive. So when I attach the chlorine to it, I need to form a more stable complex. Now, at first we might think that the chlorine is going to go to the side that's least bulky, so the side with the hydrogens, and that's simply because you might think that because the chlorine is big and bulky, but it turns out that negative, when it's attaching that positive ring, needs to go to something that can handle that charge better. So a carbon that's more substituted can hold that slight positive charge better than a carbon that has hydrogens on it. So we're always going to see this form a Markovnikov type product with that pi complex when we make that alkene. And then our second step of the mechanism is just going to take that complex and put it fully on the side. So we'll have two halogens on a single carbon. Now in a situation like this, where I don't have one of those positions with hydrogens, I actually can choose that H goes on to the left Br on the right, or vice versa. And we can't actually say for sure. So when I have an internal alkyne, I actually have to take in mind that I can get both products. And that's what we're seeing here. Now, the halogens are going to go on to one of the carbons that was made up the triple bond. But since this triple bond is not symmetrical, it's an asymmetrical alkyne, we're going to have two products. And we are kind of safe to say most of the time this is a 50-50. Alright, so that gets us our first reaction. I do show that in the middle of it we're actually starting to make a Markovnikov product to show that we make this, but we're going to actually see this most of the time as one arrow. It's going to say something about HX and excess. Alright, next one is the addition of just a halogen itself. This is comparable to what we saw with alkenes, but the same type of thing pops up here as it did with HX. We really can't stop halfway through. This thing is so unstable that when this happens, this is going to keep right on going and form the quad substituted halogen. And it doesn't matter what it does. It is actually the anti-complex that's making the same type of pi complex as the HX did, but we're not actually going to see it actually stop midway through. So a better way to show either one of these is just show your triple bond, show your halogen, and methylene chloride is the go-to solvent, and we can just say this is always going to be an excess, and what's going to happen is wherever that triple bond was, you're going to put halogens all around it. Alright, so we have our second one. And just for practice, we're going to focus on this. Now, I have something from the book that shows the differences. Now, what the books wanted us to think about here on those, like on A and B, is to see that if we just add one equivalent of HBr, we're going to make a Markovnikov alkene. And it would be anti, so I'm going to have the H on one side and the Br on the other. And if it's an excess Br, the book wants us to realize that we're going to add the H's to the side with more H's, and the other side just gets double halogens. Now, there's only one problem with that. This second species is too reactive. So if I were to do this reaction with just a 1-to-1 reactant, so I'm going to write this down here. So if I had 1 mole of the alkyne and exactly 1 mole of HBr, I'm not going to get just the alkene. What I'm going to have is, yeah, there will be some out of the alkene, but some of that alkene is going to react in that vessel, and we will get some of the di-substituted equivalent. But since we have a 1-to-1 ratio, we won't be able to make all of this, so that means we're still going to have some of the unreacted species. So whenever we try to do a 1-to-1 equivalence on this one, we're going to end up with mixtures. So you're never going to see that. We're always going to do this in excess. If we need an alkene like this, we're going to have to figure out a different way of making it. And we'll see that here later on. Alright, so that same type of logic kind of applies with C and D. We're never going to see this as just a single equivalent. So a better way to see C is to actually see that this is going to say excess in front of it. Because what I want you to realize is that's the only way we can really do these. And all we're going to do in that case is take where that triple bond is and add bromines all the way around it. And it doesn't matter if it's an internal alkyne like C or a terminal alkyne. You're still going to do the same type of thing. All around where that triple bond was is going to be bromines. Alright, now E and F, they are all excess. So what I want you to realize on the excess is we're going to make the first hydrogen go to the side that has more hydrogens. On both E and F, neither side have more hydrogens. So we have to look at what we have, because we're going to end up with mixtures if we have unsymmetrical alkynes. What I mean by that, unsymmetrical, if you look at E, that is 2-butyne. Doesn't matter if I go this way or from the other side. That is, the triple bond starts at the second position. What that kind of translates to is the only possible product I'm going to have is going to have hydrogens on one of those, bromine on the other. Or I'm going to have the mirror of that and put the bromines on the carbon on the left and hydrogens on the carbon on the right. But either way, I end up with a 2,2-dibromo, because I'd start numbering on this end because of the substitution. Alright, but on F, I have the second carbon, or I have 1, 2, third carbon. Since it's an unsymmetrical alkyne, I end up with 2 products. I could put the H's on the first one, bromines on the second, and end up with 3,3-dibromo, or put H's on the second carbon and bromines on the first and get 2,2-dibromo. So watch out for those asymmetrical carbons, because we essentially get this as a 50%, 50%. So you're going to end up with mixtures if you use an asymmetrical alkyne. Alright, next reaction is equivalent to what we saw before. We're going to add water. Now we saw with our alkenes, if we add water, we needed an acid catalyst, and you made alcohols. Well, we kind of get the same thing when we use an alkyne. The water and the is actually going to be catalyzed with an acid. So we're going to put the OH with the side with the most stable cation, and the H with the side with the most H's. But that creates what we call an enol. And OHs attached to vinyl positions are not stable at all, and they will automatically rearrange on them by themselves to, we call it a keto. This one actually is a ketone. Basically, that H is going to jump here, and the double bond is going to move up there. Now, what we're seeing there is what we call a tautomerism, or tautomerization. And basically all that means is we can actually go back and forth quite easily. In this case, I have the H going here, and the double bond moving back up here. That one goes away. And almost every single case we're going to see is going to favor the keto form. Now, we really won't see any that favor the enol form until much later in the semester, but also all these are going to favor the keto form. So what this translates to is we actually never get to add a second OH. What's going to happen is, once we've done this, formed an enol by adding the H and OH to the triple bond, we're going to actually take that enol and convert it right to the keto form. Alright, so if we have a symmetrical alkyne, we can imagine we're putting the OH on one side and the H on the other. So the OH is either is going to be in the 1, 2, third position. If I put it on the other side, it would have been the 1, 2, third position. Doesn't make a difference, but what we're going to do is see that this enol completely changes to a carbonyl and makes a ketone. If I have an unsymmetrical alkyne, the O could have been on either side. So we're going to see that we get a mixture. Second position or the third position is where the carbonyl ends up. Alright, turns out we can't do this so easy if we have a terminal alkyne. Terminal alkynes just mean that we have that triple bond on the end. Turns out the enol form of that is not very stable. So getting it to happen, we have to use a catalyst. Nasty catalyst in this case is actually mercury sulfate. So we wouldn't really want to use this in the real world too often because of the mercury, but this is the only way we could make it happen. Now, we're going to form an enol, and we're going to get the ketone form. Now, here's the nice thing. We would have to worry on this because it's an unsymmetrical triple bond of the OH ending up on the first position, but turns out the mercury sulfate makes sure that it actually only goes onto one side. So we don't get mixtures here. The mercury is going to actually form a complex at first, which allows the water to attach to our triple bond easier, and we get a mercuric enol. When the mercury comes off, we have our enol form, our keto form, that's actually going to end up always forming the O on the side that's most substituted. So, basic overall structure here is you're going to have a terminal alkyne, so I'm going to put an H, I can put an R there. You have the same ingredients as you would if you're doing just any addition of water. So I'm going to have water and acid. I'm going to use H2SO4 always. And then we're just going to put down that we have mercury sulfate as a catalyst. And what's always going to happen is the side that has the R is going to be a carbonyl, and the other side becomes a CH3. Alright, if we want to reverse that, let's say I wanted this side to be the O. So I wanted that O to go to the outside. Well, if you notice, that's kind of like an anti-Markovnikov product. It turns out we have an equivalent of the boration from alkenes. It is Hydroboration-Oxidation, just like we saw before. Matter of fact, the second step is the exact same thing that we saw with the alkenes. The only thing that's different is our reagent for the first step. Instead of BH3.THF, it's R2BH. Now the R's can be just about anything. They're just alkyl groups that actually bulk up this a little bit more. It bulks it up, the THF, and we get the same type of thing where we're going to add an H and the B and the B to the other side. And then we're just going to oxidize off that B to an OH. But we're going to form an enol in all the cases where it's the boron, and therefore the O is going to be on the least substituted side of the triple bond. Now it's interesting, our book uses this example because this is a complete and utter waste of time, and a matter of fact, it's not necessary, because since this is an asymmetrical alkyne, you're so much better off just to stay water and acid, because it's going to take that triple bond and put carbonyl on one side, turn the other side into a CH2, and that is the same thing as this. So we're only going to use the R2BH.THF and the aqueous OH and hydrogen peroxide with a terminal alkyne. So we're only using special cases with terminal alkynes. We have one terminal alkyne that we're going to use the mercury. Think of it as more of a catalyst, because these conditions are, the top conditions are the same as any time. We just have to use the mercury sulfate as a catalyst. And we're going to actually make an enol that's actually going to have the H on the side with the most H's. So we're always going to get a ketone. And if we actually use boron derivative, it's R2BH.THF. And then we have our aqueous hydroxide with hydrogen peroxide. We're going to make a enol that has the OH on the side with the most H's, and therefore it's going to get turned into an aldehyde when it goes through the Tautomerization. Alright, so we got a couple cool things. We've actually seen how we can make keto groups. It's the first time we've introduced that, and we'll do some more reactions with those later on. But now we at least know how we can make some. Okay, we're going to practice this with a couple reactions. Alright, we want to take 1 butene and do acid catalyzation with water. Alright, so 1 butene, I'm going to do just the carbons. And we're doing acid catalyzed addition of water with mercury sulfate. All right, anytime we see the mercury sulfate, want to make sure it's necessary. I have a terminal alkyne, it is going to be necessary. But since this turns an alkyne into a keto, we're just going to make the most stable form of that keto. Therefore, the O is going on the more substituted carbon. The other side is just getting a bunch of H's. And I've been leaving them off, so I leave them off here. Now, the next one, it's still that 1-butene, but now we want to do boration hydroboration, or hydroboration-oxidation. So I got to add to my line because this is a two-step process. My first step is that R2BH.THF, and I'm always going to follow that up with step 2, which is aqueous hydroxide and hydrogen peroxide. And whenever we have these two going together, we're going to make that triple bond go away, turn it into a carbonyl, but the carbonyl ends up on the side that had the most hydrogens. So in this case, the end, the terminal end. Okay, addition of hydrogen is kind of interesting because it looks very much like it did before. We're going to add, if you remember alkenes, when we added hydrogens to them, they just turned into alkanes. Turns out this kind of implies that we could stop at alkenes. But if we use hydrogen with a poison palladium catalyst, we're always just going to go straight to alkanes. And it comes back to the conditions. If the conditions are favorable for an alkyne to react, then they're favorable for an alkene to react. And they're not going to stop halfway through. So if ever you actually just use that with the palladium and carbon catalyst, it's going to actually turn an alkyne into an alkane. There is, however, some ways to stop it at the alkene level. This and another step are the only way we're going to actually ever turn an alkyne directly into an alkene. Lanyard's catalyst is the first one we're looking at. Think of this as just a very special type of metal catalyst. It's poisoned. Your book does talk about what Lanyard's catalyst is, but there are a variety of them. So we're just going to use the name to refer to a catalyst that actually can stop an alkyne from reacting all the way to an alkane. What's going to happen is with Lanyard's catalyst, the hydrogen's only going to add to one of the pi bonds, and the other pi bond stays alone. So we get a 2-pentene. So we turn a pentyne into a pentene. The neat thing is this addition's always syn. So you're always going to have the hydrogens added to the one side. That's going to leave us to cis in many cases. But remember, this could be E and Z as well, so watch out for how I name it. But we're always going to see the hydrogens added to one side and one side only. There is a counterpart that actually does an anti-addition. It's sodium or lithium metals in liquid ammonia. So we'll typically see this just written as sodium, and I typically write NH3 and the -78. Because it turns out the temperature is darn important. So that liquid ammonia is necessary. It's kind of neat. This actually forms a pretty blue liquid. But what we have down here is the actual mechanism that shows what's going on. Turns out the sodium reacts with its electron. So it's more like a free radical. That electron actually gets attracted to the triple bond, and we end up with a double bond that's actually something we call a radical anion. What that means is one of the carbons is going to behave more like an anion. The other one's going to be a radical. Obviously not very stable, but this anion part is going to be nucleophilic enough it can attach to the NH3. We're going to actually see the NH3 as acting a little bit like an acid because it's going to donate an H to the structure. We're left with an NH2-. So very strong conditions for that to be favorable because that's a very, very strong base. All right, the vinyl radical is what we end up with now. Now, where they come with this name vinyl radical is we have the vinyl group, which is the double bond, but it has a radical on one location. Now, we have another sodium metal. It's going to donate another proton or another electron to our vinyl radical, and it's going to make a vinylic anion. So another anion. We have a radical anion, then we get a vinyl anion. And this anion is going to do the same thing as before. It's going to deprotonate another ammonia. And we finally get our alkyne. Now, it turns out the structure here is very important to figure out why it actually always ends up with trans, and that's what we have on this next slide. Turns out those electrons are going to want to get as far away from each other as possible. The electron repulsion makes sure that those positions stay trans to one another. So because they stay trans to one another, both the times we add hydrogens, the hydrogens add trans. So that's important. The hydrogens add trans in this case. Alright, so that is our next thing to our table. We're going to actually be able to take our triple bond and turn it into just a double bond. We can get cis if we use Linyard's catalyst. We can get trans or an anti-addition if we use sodium with the liquid ammonia. Alright, so some more practice. Alright, now the first one here is actually kind of easy because it's just hydrogen and palladium catalysts. Since we are always going to say this is always excess, there's never anything but that, all we're going to see is that's going to turn all of these carbons that are part of the triple bonds, it's going to put as many protons around it as it can. So each of those turns into CH2, the rest of this stays the same. Now, Linyard's catalyst and the liquid ammonia with the metal in there is actually just going to add H's to just part of our triple bond. It's going to turn it into a double bond. Linyard's going to make sure this is cis. The sodium with the liquid ammonia is going to make sure this is trans. The rest of the molecule kind of stays the same, but we are turning those into alkenes. Alright, on D, we have our boron, so we have the hydroboration thing. So all we're going to remember is that's going to take our triple bond and put a carbonyl, or a carbon double bond into the O on the end. The other side becomes just a CH2. Now E, they're trying to say the same thing, but I really don't need any of this. Matter of fact, this won't do anything because I don't have a side with more hydrogens. So this would be much more useful if it had just said, instead of all that, we just said H2SO4 and water. Because we would end up with mixtures because we put an O on one side or an O on the other, but we don't need to actually do boration hydroboration. It, matter of fact, doesn't give us anything different. And the final one is just that we just saw. So we do see that it is an asymmetrical carbonyl, so we do get mixtures. We're either going to have the carbonyl in that first position, and the other side is a CH2, or the first position becomes a CH2, second one's a carbonyl, and the rest stays the same. But F, we're getting mixtures. Okay, on to something kind of neat we can do. We just saw how the reactions we can do with alkynes. Now we're going to see how we can make some of them. Now we're going to play off something kind of cool. The pKa of that triple bond actually drops dramatically. We're still not acidic, but we're a heck of a lot more acidic than our alkenes or alkanes. So we can do something kind of cool. And a strong enough base, we can have the alkynes donate protons. Now that's very specific. The triple bond must have an H on it, because if we actually put our groups on either side, the pKa's go back to being close to alkanes or alkenes, because we don't necessarily have a guaranteed sp carbon and just an AR. So we really do need a terminal alkyne for this to be a situation we can take advantage of. And what I mean by advantage, turns out sodium amide, or just the amide ion, is actually a strong enough base that it will deprotonate that, and we make what we call an acetylide ion. It's just actually, the R doesn't matter what it is, but if we have a terminal alkyne, we can deprotonate it. Now, I can't do that with OH. Some books will show OH does do some, because it does actually make some of the acetylide ions, but we actually strongly favor the reactant, so it doesn't make much. So we will actually see this gets used as sodium amide a lot more often. Alright, where this kind of comes in handy is once we've actually deprotonated it, And once we actually put it in charge, we're actually a little bit more basic than ammonia. So what we have is this wonderful thing that we actually can turn that into a very strong nucleophile. This has that lone pair on it. And now what we can do is take an alkyl halide, RX, and we can essentially have the R act as an electrophile to that nucleophile. So we just basically substitute that negative charge for whatever our group is. So it's kind of weird. We're going to make alkynes from smaller alkynes. We'll add to this as we build up our functional group lessons, but right now that's all we're looking at. We're actually going to make alkynes from smaller alkynes. Now this needs to be something special. Turns out this alkyl halide isn't just an RX. The R is something special. We need that R to be a primary or less. So see how this one is a primary carbon that's attached to our halogen? The only thing that would actually do a better job is if we had CH3 connected to a halogen. So we're going to see something kind of neat. So what we're seeing is we're going to do all these always in a two-step process. We'll start with a terminal alkyne. And our first step would always be the same. We're going to add some sodium amide. It's the base of choice to deprotonate an alkyne, a terminal alkyne. And then we're going to have a primary alkyl halide that's attached to a halogen. And whatever that primary alkyl halide is going to end up attached where that H was. Okay. This is how something like that would look. Have that sodium amide, have a primary alkyl halide, now we get a longer chain. All right. Now that we can actually make some longer chain alkynes, and we can actually do some things with alkynes, we're going to start introducing multi-step synthesis. Now what I mean by multi-step is it actually is going to be multiple steps. Now these are going to get much more involved as we get further and further in, as we learn more and more reactions, but we're going to actually follow the same basic premise all along when we actually try to figure out what's going on. We're actually just going to use all of our reactions we have memorized and figure out how we can build it. Now this is kind of interesting. We're starting with 1-butene, and if you look, I have a keto. We're not going to be able to name this yet, but you notice it has 6 carbons. Alright, so when we actually want to take 4 and increase it to 6, and then put a carbonyl in there, we must be able to do that in multiple steps, because we haven't seen anything at all like that. Alright, so the book introduces a concept of thinking backwards. And the reason why they're doing that right now, and it does make sense right now, if you think about all the stuff we've introduced in this chapter, we've done a lot of stuff with that triple bond. And that actually opens the door to too many things. There's too many things we can do to a triple bond. However, if we are thinking backwards, there's really only one way that we've made a carbonyl. And for this one, we either would have had a triple bond on this side or a triple bond on this side. So there's 2 ways we could have done that. Let me draw these out. So if we had this alkyne, we could have done with our acid and the water. And actually ended up with this as a main product. And the other thing we could have done is a second alkyne. And done the same thing with the same ingredients. Alright, so we have 2 different ways we could have made that. Now one of these looks a lot better if we stop and think about when we actually were to make this. Because if we were to do this with this 2-hexyne, we would have ended up with mixtures. We would have got the product we want, plus we would have put O's on this side. And we don't like mixtures, and so we might look at the second molecule we came up with. You notice this is 3-hexyne. I could have put the O on this side or the O on that side, which would have been the same thing. So because of that thinking backwards, or looking at the functional group we only have one way of making, we actually can deduce that this would be a better actual product to have prior to making the final product. Alright, so now we just got to ask, do we have a more simple direction to go from the 1-butene to a 3-hexyne? Now, ignoring the numbers, we do, because it turns out carbon, 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 carbon. So we just need to turn this H into that. Alright, so that gives us our starting thing. We're going to be able to do this if just 2 reactions. What we're going to actually do is use some sodium amide and the ethyl halogen to make the 3-hexyne. Then once we have our 3-hexyne, we'll just use water and the sulfuric acid to actually make our carbonyl, our ketone. Now that thinking backwards is what actually gets it. So the overall reaction is something like this bottom one. I think I said 2 reactions, but I guess it's technically 3 because got sodium amide, then the alkyl halide, and then water and acid. But we're always going to kind of do this as one thing because there's no purpose to add sodium amide at any point up to now except to deprotonate an alkyne. Alright, so let's practice another one of these. We're going to turn a hexyne into a bromopentane. Alright, again, about the only thing we can do is make this thing longer, or we can actually do bromines on it or whatnot. So we're going to try to do the same type of thing where we're going to think backwards. Alright, now we have a small problem with this if we want to think backwards. We don't have any means of taking an alkyne and adding a single bromine to it. We can take an alkyne and add 2 bromines to it. They would have been geminal. We could have added 4 bromines to it and had the disubstituted if we used bromines, but we couldn't have a situation where we only add 1 bromine to it. So we're not going to be able to do that with just one step. So we got to think, what can we do? And we do have a means of putting just a single bromine onto a molecule, and that was if we start with a double bond. Now, I'm going to actually go ahead and make a call here. Let's make our double bond terminal. Because if we do it terminal, then adding HBr, the H is going to go with the side with more H's, bromine is going to go with the side with more bromines. So that gives us our forward reaction with just HBr. Alright, so can we make this alkene from that alkyne? Well, not directly, because alkynes, to make them longer, we actually had to keep them into other alkynes. So we're going to turn this into an alkyne. So how could we have actually got an alkyne to turn into an alkene? There's actually 2 ways. And in this case, it doesn't matter which one we use. Oops. That H should not be there. The reason that does matter is because this doesn't matter if it's cis or trans. So I'm going to use linear catalysts with the hydrogen, and that's mainly because I don't want to go down to 78 degrees below 0. And now, our first step to go from our ethene to this particular alkyne, I'm just going to, first step, sodium amide. And then I'm going to use an alkyl halide. And my alkyl halide is going to have that part of the molecule attached. So CH2, CH2, CH3. Okay, another practice. Alright, we're going to take an alkyl halide, and we're going to take a terminal alkyne, and we want to make this. Alright, here's something interesting. If we think about what's going on here, the only thing we could really do with these 2 is just take some sodium amide, deprotonate this thing, and then this other R would add to it. Alright, now, this structure we can make from those two doesn't look anything like this right now. So I need to actually find where the triple bond was, because I can actually just do hydrogen and that poison carbon catalyst, and I could end up with this. But where was the triple bond? Because I need to know that to figure out what my R's were. Alright, what really pays off on understanding what goes on here is just to remember that hydrogen with palladium catalyst is going to turn any triple bond into a single bond. And how does it do that? It adds H's to both those locations where that pi bond was. Or, something that really helps us out, it's going to form a CH2CH2. So kind of what that tells us is the triple bond was somewhere among those three positions. And fortunately, it doesn't matter which three we actually choose. So what I'm going to do is say, alright, the triple bond was there. So I'm going to work backwards again. I'm going to use the hydrogen with the poison palladium to have formed my final product from this alkyne. And that should not be a 2. Oh. Alright, so now I need to actually show how I made this from my two different components. So what I need to realize is that is one of my R's, and that is my other R. Now you might think it doesn't matter, because I just need to add a, I keep bumping my keys wrong. You think it doesn't matter what my R's are, because I just need to actually connect one of these R's where that H was. But there's something about this one that's very important. And if we remember, it said it needed to be primary or just a methyl halide. The primary is a key part, because see how this R is a secondary? That one can't be the alkyl halide. It won't actually be attached to this. So that does mean that my triple bond must have originally been on beside with the secondary position. And the R prime is this guy over here. So that was bromine attached to a CH2, CH, CH3, and CH3. Alright, that gets us ready to do some more of the practice. Maybe we'll look at some of these in the class. But we actually have finished up all of Chapter 8. There is some more in the back of the book, some more of the retrosynthesis. But I believe that since the book goes over them very well, it's a great little thing for you to study to make sure it makes sense to you. And I would encourage you to do some of the problems in the back of this book that are more of the retrosynthesis, just for the sheer practice of them. And that concludes the recording.